We are going to start from this lecture, the second unit of our syllabus. The first thing which we are going to learn in this second unit is a new problem of conduction. A new addition is there in this problem as compared to the previous problem. In the previous problem, we have seen that the heat was getting conducted through the material without any internal energy generation, and we can apply the generalized conduction equation to this situation. We can reduce it, we can find out the solution, and subsequently the solution was converted into a simple methodology called as electrical analogy. And we have solved many problems using the electrical analogy in order to find out the rate of heat transfer in a given cylindrical, spherical as well as plane wall systems. Now we'll add one thing in this problem. That is, the problem is not without heat generation, it is going to be with some internal heat generation. So what is the change because of this particular thing, because of this particular addition into the solution, and how we can tackle such type of situation in practice, and what are the practical examples of such type of problems that we are going to see in this particular lecture. Before we start this lecture, I'd like to remind you that whatever content I'm going to cover this in this lecture is relevant to be studied only after understanding the concepts of boundary conditions. So I request you to revisit my lecture on the boundary conditions, the applications of the boundary conditions, and then start fresh of this video, because whatever boundary conditions I have covered, I'm going to utilize those boundary conditions here. I'll start with some introductory remarks, then we'll start about heat generation in the plane wall, how we can tackle this problem, cylinder and sphere. And then we'll see some of the numericals, some of the problems with which solution of the problems for heat generation. Okay. Myself, Nitin L. Berur, working as Associate Professor in Sandeep Institute of Engineering and Management. Heat generation, till now, we consider the conduction problem for which the temperature distribution was dependent on the condition at the boundary of the medium. There was no internal generation of energy. Now, the effect of thermal energy which is generated within the object on the temperature distribution is to be considered. So, without heat generation, now we are starting with heat generation. For example, consider a conversion from electrical to thermal energy. Now, how this thermal energy is getting generated? As usual, whenever thermal energy is getting generated or heat is getting generated, it is actually getting converted from some form. Maybe like electrical energy. Electrical energy, because of the resistance offered by the conductor, current carrying conductor, is getting generated, and inside the conductor, the rate at which the heat is generated in the conductor of electrical resistance Re is the rate of generation, that is E dot G is I square Re, where I stands for the current. So square of current into the electrical resistance is the amount of energy generated in watt from for any electrical resistive circuit. Then if this energy generation, whatever is energy generating, power generating, occurs uniformly throughout the medium of volume V, if the volume of that conductor through which this energy is getting generated of the magnitude of I square Re, if this energy generated is uniform throughout the medium, and if the volume of that medium is V, the volumetric rate of generation in watt per meter cube can be specified by using a simple equation, that is the rate of generation divided by volume. So I square Re divided by V. So this is what is called as Q dot, and we already defined this Q dot when we are talking about the generalized conduction equation. It is the volumetric generation rate and expressed in watt per meter cube. So we are going to consider this Q dot now into our consideration. So you can just recall the generalized conduction equation, one dimensional generalized conduction equation with internal heat generation under steady conditions. So we are not going to consider the unsteady conditions now, we will consider the steady conditions. So some examples of the heat generation are resistance heating in the wire, exothermic chemical reactions in the solids, chemical industries, then nuclear reactions in the nuclear fuel rods, where electrical, chemical, and nuclear energies are converted into heat. Ripening of the fruits. During the ripening of the fruits also, some energy is getting generated which is dissipated from the skins of the fruits. So that is also another example of heat generation problem. So not only from the engineering field, the applications of the heat generation are there in the other fields also. Then whenever such type of exothermic reactions, chemical reactions are taking place, nuclear reactions are taking place, resistance heating is taken place, some form of energy, which say electrical, chemical or nuclear energy are converted into heat. Means that object is now not only conducting the heat, it is also generating some energy. The examples are shown in this picture. Now, another example is the absorption of radiation throughout the volume of semi-transparent medium like water can also be considered as heat generation within the medium. If the solar radiations are incident upon a lake, and if the lake is non-moving, means the water is non-moving, it is semi-transparent medium like water, and the absorption is uniform. The solar energy which is incident is having uniform intensity, then then also can be considered as heat generation within the medium. Although it is coming from outside, it can be considered as generation within the medium. So that is also an example of heat generation problem. Now let us apply the heat generation principles to different types of coordinate systems: plane wall, cylindrical system and spherical system. So consider first a plane wall in which there is uniform energy generation per unit volume. For constant thermal conductivity K, the appropriate form of energy equation, I am once again reminding you, one dimensional steady state conduction with internal heat generation. So if you reduce the generalized conduction equation in Cartesian coordinate system for one dimensional steady state conduction with internal heat generation, you will get this. Without internal heat generation, only d square T upon dx square is equal to 0 was the equation which was solved in the first case. Now we are talking about the heat generation, so we are considering this term, additional term Q dot upon K. Now, as usual, in order to find out the solution, the next step would be to integrate this equation. And as we know that integrating this equation gives us the temperature gradient equation. So temperature gradient equation, if you integrate this equation by bringing this Q dot by K on this side, it will become dt upon dx is equal to minus Q dot upon K into x plus the constant of integration C1. So this is the temperature gradient equation for a plane wall with energy generation. Now once again, if you integrate it, again integrating, the general solution for the temperature distribution is obtained, that is the temperature distribution equation is obtained, and it is in the form like this. So reintegration is T is equal to minus Q dot upon 2K into x square plus C1x plus C2. Now you can recall our understanding of this type of situation, that is the temperature gradient equation. If you want to find out the rate of heat transfer at any location, we need to find out the temperature gradient, and this temperature gradient is to be used along with the Fourier's law of conduction for finding out the heat transfer rate. So for finding out the temperature gradient in a plane wall, we need the value of C1. Then in order to find out the temperature at any point within the plane wall, we need the values of C1 and C2. Now, in order to get these values of C1 and C2, we have to use appropriate boundary condition. It may be known temperature boundary condition, it may be known flux boundary condition, convective boundary condition, symmetrical boundary conditions, insulated wall boundary conditions, or it may be radiative type of boundary condition. So with this all these boundary conditions, we can solve this problem, and we can calculate the rate of heat transfer and the temperature uh, distribution using the temperature gradient and the Fourier's law. So this was already done for the previous problem. We can equally apply these boundary conditions in this case also. Now let us see some of the boundary conditions. Let's take a review of the boundary conditions considering a plane wall. We've already seen this. Yes, I'm revising the things. Uh, it is possible to have asymmetrical boundary condition. Asymmetrical boundary condition means on the both the sides there are different fluids with different temperatures, T infinity 1 and T infinity 2, and the different heat transfer coefficients. So we are not having any information about where this maximum temperature is going to get occur. And additional thing is that this object is now, instead of only conducting, it is generating the heat at Q dot watt per meter cube. So what we can see in this case, that in this case, either if you know the values of this Ts1 and Ts2, that is the surface temperature at 1 and surface temperature at point 2, for this particular thing, we can write at x is equal to minus L, the temperature is equal to Ts1, x is equal to plus L, the temperature is equal to Ts2, like that. Or if you don't know the values of Ts1 and Ts2, we can put it in terms of the convective heat transfer at the respective ends. So at x is equal to minus L, rate of conduction is equal to rate of convection. At x is equal to plus L, rate of convection is equal to rate of conduction. So you can recall to the boundary conditions and how we have applied it for the different situation. Now symmetrical, it's possible that this boundary condition can be more simplified. If we are having same side, both on both the sides same fluid with same heat transfer coefficient, or if the surfaces of the two sides of the wall are maintained at same temperature, so that is becomes symmetry, and we know that at the when it is symmetry at the center, we are getting the maximum condition, maximum temperature, and we can use that as a boundary condition. So that is possible in symmetrical boundary condition. Third possible is of course the insulated boundary condition. Here you can see this particular surface is insulated, so the heat transfer from this surface is prevented, and because of that the temperature gradient at this location is zero. So we can use this as a boundary condition. On the other side, of course, we can see that here rate of conduction is equal to rate of convection. So this type of boundary condition we have already seen. We have seen them in detail. We have seen their applications in detail. So the same boundary conditions are to be applied for this particular type of plane walls. Okay, so we can use these boundary conditions now for finding out the temperature distribution as well as the heat transfer rates. In the cylinder also, we can consider a cylinder in which there is uniform heat generation per unit volume, and for once again the constant thermal conductivity. The appropriate form of the heat equation would be 1 upon R d upon dr in bracket R dt upon dr. This was for radial direction heat transfer plus the heat generation term Q dot upon K is equal to 0. So once again, if you are to find out the temperature gradient equation, we have to integrate this equation. We'll get this, that is dt upon dr is equal to minus Q dot upon 2K into R plus C1 upon R, and that is our next equation. And once again we can reintegrate it for getting the general solution in the form of temperature distribution equation, and that would be temperature in the radial direction is equal to minus Q upon Q dot actually divided by 4K R square plus C1 natural log of R plus C2. So this is our next equation. Once again we can use the appropriate boundary conditions and we can solve the problem. In this case of sphere also, the same procedure can be repeated. The constant thermal conductivity, appropriate form of equation is 1 upon r square d upon dr r square dt upon dr plus q dot upon k. Integration of this equation will use the temperature gradient equation, that is dt upon dr is equal to minus q dot upon 3k r plus c1 upon r square. It is c1 upon r square, that sign is missing. Then again integrating, the general solution for the temperature distribution can be this fashion. Temperature at r is equal to minus q upon 6k r square minus c1 upon r plus c2. So we can once again apply the boundary conditions as per the requirement and find out the solution for this. So what we have seen till now is how we can use the generalized conduction equation, reduce it to the required form of one dimensional steady state conduction with heat generation, and how we can convert those equations into the temperature distribution equation and temperature gradient equation for cylindrical, spherical as well as Cartesian coordinate system. Now we'll see some of the examples how we can proceed further for finding out the values of C1 and C2 by using some simplified boundary conditions. So let us see it. So let us take a first example of plane wall with known temperature. The plane wall is there, the temperature of the surface is known. Then how we can solve this problem? Let us consider a plane wall of thickness 2L. Note that it is 2L, not L. Just for simplicity, it's taken at 2L, because when you are taking 2L, we can take the center point, center plane as the origin plane, and on both the sides of the center plane, it will be minus L plus L. So that simplifies the problem, that simplifies the calculation. That's why normally when we are considering a plane wall, we are taking it as 2L thickness. Whatever thickness is there, we are calling it as 2L, in which there is uniform energy generation per unit volume and the surfaces are maintained at TS1 and TS2. Let us consider the problem. So we have got a plane wall having thickness 2L, thermal conductivity K, uniform generation is there Q dot, surface 1 at x is equal to minus L is maintained at TS1, at x is equal to plus L is maintained at TS2. So what are our boundary conditions now? At x is equal to minus L, temperature is equal to TS1, at x is equal to plus L, temperature is equal to TS2. So these are our simple boundary conditions for solving the problem. So let us uh, write down the appropriate form of the equation, then the temperature gradient equation and the temperature distribution equation, as we have already done this. Now we'll use the boundary condition where C1 and C2 are the constants of the integration. Now taking the center plane as origin plane, I already told you why we are doing this. For the prescribed boundary condition, now what are the boundary conditions? Temperature at x is equal to minus L, it's TS1, and temperature at x is equal to plus L is TS2. So if we employ these boundary conditions, of course, we have to substitute in the temperature distribution equation. So the constants may be evaluated, and these constants are in this form: C1 is equal to TS2 minus TS1 divided by 2L, and C2 is equal to Q dot upon 2K L square plus TS1 plus TS2 divided by 2. So you can do all these calculations and find out the values of C1 and C2. And if you substitute these values of C1 and C2 in the temperature distribution equation, the temperature distribution equation will become like this. So this is the equation which can be used for finding out the temperature at any value of x. So if you know the value of x, you can put simply the value of x in this equation here, and all these other things are constant. So we can use that and find out the temperature at any location. Now we can substitute the value of C1 into temperature gradient equation, and we'll get the temperature gradient as equal to minus q dot upon k into x plus ts2 minus ts1 divided by 2l. Now this temperature gradient, because we know that rate of heat transfer is minus k a into dt by dx, and heat flux at any point is k minus k into dt by dx. So dt by dx is there, you have to just simply multiply this by minus k and put the value of appropriate value of x where you want to find out the heat flux, and directly you can calculate the heat flux at that particular location. So this is how we can solve the problems of finding out the rate of heat transfer as well as temperature distribution if the heat generation is involved. Of course, the equations which we are getting are little bit more complicated, but they are not difficult, and you do not to remember the equations. It is not expected from the students to remember the equation. Only what you need to remember are the basic form of the governing equation. You can integrate it to get the temperature gradient as well as temperature distribution equation, you can put the appropriate boundary conditions. You can calculate the values of C1 and C2, and then it's a matter of just substitution of the values of C1 and C2 into temperature gradient equation and temperature distribution equation, and you can find out the appropriate results. You can find out the temperatures at any location. You can find out the temperature at, or sorry, heat flux at any location, or you can find out the maximum value of temperature also, means Tmax. How to find out Tmax? Tmax is the location where dt by dx is equal to 0. So you have to just put dt by dx is equal to 0 and find out that value of x, and then put that value of x into temperature distribution equation to get the maximum value of the temperature. So you can find out the location of the maximum temperature by just equating dt by dx is equal to 0. So it's a simple process, simple mathematical process. Only some calculations are a bit complicated, but I think you can manage it. It's not so difficult. Now, this results, whatever we obtain, can be more simplified if both the surfaces are maintained at same temperature. Means if there is existence of thermal symmetry. If the surfaces are maintained at same temperature, we can get the temperature distribution is going to be symmetrical in this case, and about, of course, the mid plane, and the temperature distribution will be, if you repeat the procedure of calculations of all the C1, C2 and this, you'll get the final form that temperature at x is equal to minus q L square upon 2k in bracket 1 upon, oh sorry, 1 minus x square upon L square plus T. Now you can see that this equation is rather simplified as compared to the previous equation of the temperature distribution, simply because of now there is existence of thermal symmetry. Now the maximum temperature, once again, as I told you in the last slide also, we can calculate the maximum temperature by first finding out the location. Now here already we know that the temperature distribution is symmetrical, so the temperature at the mid plane is going to the maximum temperature. So if you find out x is equal to, if you put x is equal to 0 in this situation, you'll get the temperature at the mid plane like this. Okay, so this is how we can find out the different types of temperatures and the heat fluxes at the location. Now let us do it. It is important to note that the plane of symmetry, and therefore the temperature gradient is 0 at x is equal to 0, and there is no heat transfer across this plane, because that's why only we are saying that the maximum temperature is there, exist at the mid plane. So we can take another example of a radial system, and I'll show you how the equations are developed for the radial systems, and you can use these radiations or the radial system equations or the previous plane wall equation for solving the numerical problems. Consider a long solid cylinder. Outer radius of the cylinder is RO and the length is L as shown in the figure. Of course, the length is I have not shown. I'm just showing you the front view of this. The radius is RO, and in the radial direction heat transfer is going to be there. This cylinder is in contact with the fluid with heat transfer coefficient H and temperature of T infinity, and the rate of heat generation within the object is Q. Thermal conductivity of the material is K, and the outside surface, because of this heat transfer, is now maintained at some temperature Ts. So when we are having a uniform heat generation throughout the cylinder and it is exposed to a medium having temperature T infinity, the heat transfer coefficient is H, then under steady state condition we can employ the energy balance, and simple energy balance will yield into the rate at which the heat is generated within the cylinder. Whatever is the generation rate in the cylinder, it must be equal to the rate at which the heat is convected from the surface, because if whatever is generation and if it is not convected, then it will become the problem of unsteady condition. It will result into change in temperature with respect to time, which is not a condition for a steady condition. For steady condition, temperature must be same with respect to time, and that's why the rate of heat transfer must be same, and that's why in this case, as it is heat is getting generated, that same heat amount, whatever is energy is getting generated, the same is to be dissipated same time, so that the temperatures are not going to change with respect to time. So under steady conditions, I can say that the rate of heat generated within the cylinder must be equal to the rate at which the heat is convected from the surface of the cylinder to the moving fluid. So this condition allows the surface temperature to be maintained at a fixed value, that is T. So if this heat steady condition is there, automatically the Ts is going to be a constant value. So let us solve this numerical, solve this particular situation. To determine the temperature distribution, appropriate form of equation is this. Then the temperature gradient equation is this. Already we have done this, and once again it can be integrated to give the temperature gradient, sorry, temperature distribution equation. So we got all the equations now. Now we have to obtain the values of C1 and C2. We need to apply the boundary conditions. And what is the boundary condition? Here there is existence of thermal symmetry. The first condition results from the symmetry. That is, for a solid cylinder, the center line is a line of symmetry. Whenever we are solving a problem of same cylinder or sphere, solid cylinder or solid sphere, always there is existence of this type of thermal symmetry. And the center line is a line of symmetry for the temperature distribution, and temperature gradient at the center must be equal to 0. That is because of the symmetrical condition. So we can use this as a boundary condition, that dt upon dr at r is equal to 0 is equal to 0. So the temperature gradient at the center line is equal to 0. So that is the meaning of this particular term. So you apply, put this from the symmetry condition, r is equal to 0, and put it in the temperature gradient equation, you will get C1 is equal to 0. So what is our first result? First result is C1 is equal to 0. Now using the surface boundary condition, that is at R is equal to RO, that is outer radius. What is the condition? The surface temperature is Ts. That is, temperature at R is equal to R0 is Ts. And if you use this boundary condition, then you will get C2 is equal to Ts plus Q dot upon 4K into RO square. So we got C1 is equal to 0, C2 is equal to this. You can use this these values of C1 and C2 into the temperature distribution, and the temperature distribution will take this type of form. It is will become Ts plus Q dot R0 square upon 4K in bracket 1 minus R upon R. So whatever at any radius R, you can find out the value of temperature up to R0. So we can put the value of R right from 0 to R0. Now if you put R is equal to 0, in this case you will get the maximum temperature, of course, because it is at the center line. The heat rate at the outer surface in the cylinder may be evaluated by using the temperature gradient equation with the Fourier's law. Remember that C1 is equal to 0. So in the temperature gradient equation, C1 is there. You have to just substitute C1 is equal to 0. Automatically you will get the temperature gradient equation without any arbitrary constant, and you can use it along with the Fourier's law of conduction, that is minus k dt by dx, and you can find out the rate of heat transfer, and the equation will be like this. So the temperature, if you calculate it, you will get this Q dot into pi R0 square into L. So this is how the heat transfer rate can be evaluated at outer radius. Now the surface temperature can be related with the temperature of the fluid, because uh, subsequently whatever energy is getting generated, that energy is convected to the fluid. So we can say, by using that energy balance, that rate of generation is equal to rate of heat convection, we can surface energy balance. Heat is conducted outer surface of the cylinder must be equal to the rate at which is convected from the surface, and we can obtain this. So this is rate of generation, and this is the rate of convection. This is the volume of the object, pi R0 square into L. So Q dot is watt per meter cube multiplied by volume, will get the rate of heat generation, and that rate of heat generation must be equal to rate of heat transfer. So this is surface area, 2 pi R0 into L into Ts minus T infinity. So if you put this, you can simplify this equation in this fashion. If you cancel out the common terms, it will be Ts is equal to T infinity plus Q dot R upon 2H. So you can find out the value of surface temperature by using this simple equation. Now I would like to add one word of caution for this. Whatever equations we have derived, we have written for the plane wall and for the cylinder system, except those the temperature gradient equation, temperature distribution equation, and the general form of the equations. All other equations are dependent on the respective boundary condition. So don't use them for all the types of situation. This particular equation, whatever I have written, is applicable only when there is existence of thermal symmetry and there is a convective boundary condition. So this is a word of caution. So you cannot use this equation anywhere. Of course, in most of the situation you find that in a cylinder there is thermal symmetry and the cylinders are subjected to convective boundary condition. So that in those situations you can use this equation for your solution of the problem. But this is not a general equation to be used for all the types, all the problems of cylinder and sphere, of course. So in this lecture, we have learned about the heat generation concepts, where what are the applications of heat generation. We have seen the heat generation in plane wall cylinders and sphere, how the equations are converted into temperature gradient equation and temperature distribution equations, and we have seen some of the problems. And we have solved some of the problems of heat generation for different types of boundary conditions. Thank you. Thank you very much.